Okay, suppose we have a data in observation from 1 to n, a set data, which is random RID independent and identically distributed. This is a RID random draws from a distribution, normal distribution with mean mu and the standard deviation 1. And so here's one point here. So frequently I'm going to use, say, capital Y to denote the random variables. For example, y1, y2 until yn. And little y to denote its realizations. So little y1, little y2 until little yn. Okay. Okay, so now we have this set of data. And our aim is, we know they are coming from these normal distributions, but we don't know what mu is. So our aim is to estimate mu from this data we have in hand. How can we do that? Certainly there are different ways of doing so, but one way we can do is, okay, let's find out what's the probability of observing these samples. We should expect that this probability already depends on the mean mu, on the unknown mu. So if we know this probability, we can choose mu to maximize. Choose mu to maximize this probability. Right. Okay, let's derive the probability first. So we know that these data, these samples, they are independent. Okay, so we only use this independency. So this is exactly the same as yi, so the random variable y, big yi is equal to little yi, for I is equal to 1 until n, observing these samples. And this is just the same as, okay, y1 is equal to little y1, and y2, big y2 is equal to little y2, and this big y1 until yn, they have the same distribution as y's, which is normally mu1. Okay, normal distributions. And now, because all these events are independent of each other, we can write it this way. Times probability of y2 is equal to y2 times probability of or more compactly is this. Okay, so now for these terms, we're going to replace this probability by the PDF of yi. And we know that yi is normally distributed with mean mu and standard deviation 1. So this means that its PDF probability density function is just this. minus mu square divided by 2. Okay, let's plug this one into here. So now this probability is equal to multiplication from 1 to n of 1 over root 2 pi e raised to the power negative 2 y minus mu squared. And we see that this probability indeed depends on mu. So ideally, we want to choose a mu to maximize this probability. And actually, we call this maximum likelihood estimator. Okay, so now to make our life easier, let's take log at both sides. So log is a linear monotone increasing transformation. So we maximize the probability will be the same as maximizing the log of the probabilities. So let's call this ln L. L is likelihood. Take log at both sides, so this multiplication becomes sum. We get log 1 over root 2 pi minus y minus mu square divided by 2. And this is so put this one inside. So we get n times log 1 over root 2 pi minus 1 over 2. Okay, so now we want to choose mu. So choose mu to maximize ln L, which is a function of mu. And observe that this function is actually a nice function in a sense because its quadratic form is easy to maximize. Okay, let's look at the first order condition. Differentiate log likelihood with respect to mu. So the first term here does not depend on mu. So it drops. So there's a mu here. Okay, minus 1 over 2. So there's a square here. This y minus mu raised to the power of 2. So we can put the power down. Take 1 away from power. Then there's negative 1 here. Okay. So this negative cancels out with this negative. So it's and move 2 out. Cancel out with this. So we get this. And there's no square here. All got this one. Set to 0. Okay. So this implies that n mu is equal to sum of this yi, or mu 1 over n y. And we are going to put a head on top of this because to denote that this is an estimator. Maximum likelihood estimators. Okay. And if you look at these terms carefully enough, you should see that this is just the average. The average of yi. Okay. So now the next question that you want to ask. Okay, we have these estimators. maximum likelihood estimators. How good it is. You should know that I'm speaking a language I'm speaking a vague language. Okay, what do I mean by good? Okay, here's what we mean by good. So what we want, if we have sample size increase to very big, infinity, we want this mu hat, this estimator converge to mu in a sense, or in probability actually, at least. Okay, and we know that this is the estimator is the average actually. We have a theorem called law of large number, guarantee that this converge in probability to the underlying mean. Okay, this is the idea of maximum likelihood estimators.